In this video, we'll be talking about probably the most famous distribution that most people learn about at a very, usually early age. They kind of get a notion of it, the normal distribution. So this is kind of what people think of when they say the bell curve, the one that usually looks like this, and is used for many different applications and things like that. So it's usually should be more symmetric than that. But okay, so we say that a random variable x is distributed as normal with two parameters, mu and sigma squared. So since this is sigma squared, this has to be positive. Mu, on the other hand, can be any real number. Okay, so I'll maybe make a quick note of that. Sigma squared must be greater than or equal to 0. And mu can be any real number. So we say that if it has the following PDF, and this is probably the most complicated PDF that we've seen so far, but it'll quickly become very familiar because this is used so often. So we read our familiar PDF form, f big X, and we have little x is equal to, and the thing about this PDF is that it has no other conditions. Usually we have a case where it's 0 otherwise. Here, it's just one thing and it applies to the whole real line. So it's 1 over sigma square root 2 pi e to the negative x minus mu squared all over 2 sigma squared. Okay? So it is 1 over this sigma times radical 2 pi e to the whole thing up here. Okay, so it's not too complicated, but it is more complicated than other things we've seen so far, and there's not really, we're not really going to give it an intuitive way to think about it here, so maybe that make it harder to memorize, but try to memorize it best as possible. Okay, cool, so this is it. This is on the whole real line. X can be anything from minus infinity to infinity, and indeed if you integrate this from negative infinity to infinity, you will get 1. Okay, so the next thing, we're just going to go dive right into how to find the expected value. The variance I've done on the back of this paper, we'll just trace through it, and then we'll do the moment generating function as well. Okay, so let's do the expected value first. So let me use a different color maybe. So we want to find the expected value, so we're just going to do the standard thing. Expected value of x is given by the integral negative infinity to infinity, and here we don't change the bounds because it is indeed from negative infinity to infinity. We'll write the PDF, so write the PDF, and then since we're doing the expected value, I want to put an extra x in here, dx. Okay, this looks very complicated, and there's a few tricks we're going to have to learn along the way. So let's do the simplification we can. This right here is a constant. This sigma radical 2 pi is a constant. We're going to pull it right out. 1 over sigma radical 2 pi, integral from minus infinity to infinity, e to the minus x minus mu squared over 2 sigma squared, and we have an x out here, dx. Now the next thing I want to do is make a substitution. I'm going to do a u substitution, and I'm going to go ahead and use the choice u equals x minus mu over sigma, because that is kind of what's here except it's squared. So then if I have that, I have du equals 1 over sigma dx. Okay, so now I'm ready to make my u substitution, so I have 1 over sigma radical 2 pi. Do the bounds change at all? If I put negative infinity into here for x, this is still negative infinity. If I put infinity, it's still infinity. Notice sigma is the positive square root of the sigma squared. Okay, so it's positive. So I'm still getting from minus infinity to infinity. This x becomes what? It becomes u sigma plus mu. U sigma plus mu. And then I get e to the negative u squared over 2. Okay, so that makes sense because this is, if you square this, it becomes this, except you still have to put it divided by 2. And this dx changes to what? This dx changes to a sigma du. So it changes to a du, and I'll put the sigma outside since it's constant, and it nicely cancels with the bottom sigma right there. So we have 1 over radical 2 pi as the constant that's outside. Okay, now we're going to split this as 2 integrals because there's a plus sign here. So we're going to get, on the one hand, we're going to get 1 over radical 2 pi. That's just going to be on the very outside. The first integral is going to be sigma, integral from minus infinity to infinity, of u e to the minus u squared over 2 du, which is going to be, we can use regular means to calculate this guy. And on the other hand, it's going to be plus mu, integral minus infinity to infinity, e to the negative u squared over 2 du. Okay, cool. So this guy is going to be what? We could go ahead and do our calculations, but let's notice something. This inside this integrand is an odd function because this u squared over 2 is an even function, and this makes it odd, which means that if we integrate an odd function from a negative limit to the positive limit, and the negative and positive absolute values are the same, in this case they're negative infinity and positive infinity, this whole integral will just go to 0. Okay, so that simplifies things a lot very nicely for us. So really all we have is mu over rad 2 pi, this integral. This integral, it's not clear how to do it at first, so we're going to have to do a little bit of creativity. We're going to have to use polar coordinates here. So instead of calculating this integral, let's calculate this integral squared. I know that seems weird, why would you complicate it? But we're going to see why that makes sense. So we want to calculate, I'm going to try to calculate this integral squared. So I want that integral times itself. So I'm going to write exactly that. So I'm going to write again a copy of that, except I'm going to use a different variable. And it really doesn't matter which variable I use here, because if I calculate this integral and this integral, they'll be the same, because this might be in respect to u, this might be with respect to s, but in the end they're going to have the same answer. So I'm really getting this integral squared still. Now since this ds and this du are independent, they have nothing to do with each other, I can kind of merge these guys together in the following sense. I can have a double integral, minus infinity to infinity minus infinity to infinity, e to the, and since I'm going to multiply these integrands together, I can add their exponents. So I have e to the minus u squared plus s squared, all that over 2, okay? And then I have du ds. So you're probably thinking, why did I do this? This seems like a very, just messing things up. But now we're ready to make that polar change of variables, and that change of variables, the polar change of variables will be r squared equals u squared plus s squared. So we're going to try to change this into something in the form dr d theta. So changing into polar, go back and review that if you need to, but since it's on the whole plane, negative infinity to infinity in the x and y, or in this case the u and s, it's going to be, we're going to let the outside integral be theta, so we're going over the whole circle, and the whole, this r will go from 0 to infinity. The radius is going to be from 0 to infinity, and we're going over the whole circle in the polar form. Now e, this inside becomes very nice, which is why we're doing this. It becomes e to the negative r squared over 2. And this d, remember when you change this part, it becomes r dr d theta. So we put r, and then we put dr d theta. Okay, so I run out of room, so let me grab another piece of paper. Okay, this will work nicely. So what we have here is this, and all we need to do now is just simplify this a little bit further. So we're going to have this inside part is the same kind of integral we would have evaluated up here if we wanted to evaluate it. Now we have to evaluate it. So we're going to use substitution. Let me use z instead because we've used u for something else. So we have z equals r squared over 2. Okay? So dz equals r dr. So inside we're going to have, does the integrands change at all? So 0 stays 0, infinity stays infinity. So, sorry, do the limits change at all? No, they don't. This r dr becomes a dz. And here we have e to the minus z. Okay, so this is easy to evaluate. This is just negative e to the minus z evaluated from 0 to infinity. So it's e to the, when you put e to the minus infinity, you get 0 minus 1, so this just comes out nicely as 1. So really this whole inside part right here is just 1. So really we have the integral 0 to 2 pi 1 d theta, so it's just equal to 2 pi. Now, so we found that this integral, this one right here, squared, was 2 pi. So by itself, it's just radical 2 pi. So this is radical 2 pi. And notice we have a negative, we have a radical 2 pi on the denominator to cancel that. So this cancels with this. And all that survives after all of this kind of mess is mu. And that's pretty clean. So we find that a normal distribution with parameters mu and sigma squared, if you want the mean, all you have to do is look at that first parameter. The mean is given by mu, which is kind of suggestive because mu, mean, you know, kind of it's very suggestive in its name. So that was very easily done. Now the variance, it's a similar calculation. I've done it for you. Let's walk through it. Variance, remember, is expected value of x squared minus expected value of x squared. We just found that was mu, so mu squared down here. Now we need to calculate this expected value of x squared. So I did the same exact thing. You know, I took the PDF, I multiplied by x squared here, and I've taken the constants out. I immediately made that use substitution again, x minus mu over sigma, and it became a little bit more complicated because I had to square it here. So I have split up into 3 integrals, this one, and this one. Turns out this one is the same form that goes to 0, so that went to 0 for us. Let's see. This one right here, we just calculated that. This was rad 2 pi, which is why that showed up here. And this was kind of a new integral. We didn't really know how to do it yet, but it turned out a simple integration by parts worked out if we let v equal u and dw equal u e to the negative u squared over 2 du. So that integration by parts is carried out. We see that this becomes radical 2 pi as well. So really we have 1 over radical 2 pi, sigma squared rad 2 pi plus mu squared rad 2 pi becomes very nice. sigma squared plus mu squared. Subtract the mu squared we need to subtract, and you get sigma squared is the variance. So again, look at the parameters. To find the variance, all you have to do is just look at this parameter right here. So that's the way normal distribution is defined. It's defined in terms of its mean and its standard deviation. So in a graph, for example, let's give concrete values. Let's say mu is -1. Let's say sigma is maybe 1. Okay, so that means it's centered at -1. That means this bump, which you usually think is at 0, in this case it will be at -1. So here's the actual 0, here's 1 maybe, here's -1. So that hump will be centered up here. And the bigger the standard deviation is, the more kind of spread it'll be. That's kind of a colloquial measure. It's called the spread. So maybe we'll just draw a quick picture here. So it's going to look a little bit like that, maybe. Okay, so the point is here it's centered at 1. So maybe for reference, if I had changed the sigma squared to 2 instead, it would be spread out more. So maybe, let me put this in different color. Let me attempt to do this. So if we put the mean, notice would still be at -1. So that hump would still be at -1. But now it's kind of spread out more, kind of like that, right? So it's spread out more. That's the basics of it. So now we can kind of go on and compute the moment generating function. So let's continue on this piece of paper right here where we had that. So we're trying to find the moment generating function of this normal random variable. So we could go through that whole process and make this hard on ourselves, or we could use a property of the moment generating function, and then we could just do it for the standard normal random variable. So the standard normal random variable is the normal with mean 0 and variance 1. And it turns out this has very nice properties, and it makes calculations a lot simpler for us. So we're going to work with this guy. The PDF of this guy is given by, if we plug mu equals 0 and sigma squared is 1, it's just 1 over rad 2 pi e to the negative x squared over 2. Okay, it looks a lot nicer than the general form. Now what we want to do is find the moment generating function of this guy. How do we do that? Remember, it's expected value e to the sx. So doing that, it's going to be minus infinity to infinity. Let's take the 1 over 2 pi out. We need to put e to the sx, e to the negative x squared over 2 dx. So all we have to do is some creative factoring here, and then it kind of solves itself. So 1 over rad 2 pi. Let's first just combine the exponents. We have e to the sx minus x squared over 2. We have dx. I'm going to rewrite it in the actual form, and then we'll just confirm that it's correct. So we have 1 over radical 2 pi, and I forgot my bounds here, so minus infinity to infinity, and we're going to have e to the power of negative 1/2 x minus s squared plus 1/2 s squared. Let's make sure this is correct. So if we expand this, actually let's do the expansion maybe up in this corner right here. So if we have minus 1/2 x minus s squared, that expands to negative 1/2 x squared minus 2xs plus s squared, and then we have that plus 1/2 s squared plus 1/2 s squared. So we see right off the bat, this negative 1/2 s squared, this plus 1/2 s squared cancel. So all we're left with is just this minus 1/2 x squared plus xs, and that we see is exactly what we have here. We have this sx minus 1/2 x squared. Okay, so this is correct, and it makes it nicer for us because now we can take this e to the 1/2 s squared. It had nothing to do with x, so we can just take it out. So we have 1 over rad 2 pi. We get e to the 1/2 s squared, integral negative infinity to infinity, e to the negative 1/2 x minus s squared dx. Now let's notice something. So I'm going to actually take this 1 over rad 2 pi and put it with this just so we can notice this fact. But we have e to the s squared over 2 still sitting outside, minus infinity to infinity, 1 over radical 2 pi, e to the negative s minus x squared, x minus s squared over 2 dx. Now notice this is the PDF of a normal, I'm just going to shorten normal to n for here, normal s and variance 1 random variable, right? Because the normal, this mean s shows up here, and the variance is 1, because sigma squared being 1, it would show up down here as 1 squared, and would show up here as 1. So this is exactly that. And so we're taking it over the whole real line. Since it's a probability density function, it must integrate to 1. So this whole integral must be 1. It's a very easy way to evaluate this integral. So really all we're left with is just this outside term, is e to the s squared over 2. So we've successfully found the MGF of a normal 0, 1 random variable, but that's not fully what we wanted. We wanted to find the MGF of a general normal random variable. And I've written a almost full write-up here. We're going to complete the last few steps together. So we want to find the MGF of a normal mu sigma squared. So the steps are not that hard. The real insight is the thing we just did. So at the beginning I just started by saying I wrote exactly what it is. It's 1 over sigma rad 2 pi, that's part of the PDF, negative infinity to infinity, e to the sx, that's the MGF coming in, and we have the rest of the PDF here. So I use the regular u substitution we've been using, u equals x minus mu over sigma, and I carried that through, so you can look through the algebra if you want, and I've gotten to this step here. Now this is what, if we look back at what we had, when we were finding the MGF of a normal 0, 1 random variable, we had this. We had 1 over radical 2 pi, negative infinity to infinity, e to the sx, e to the negative x squared over 2 dx. Now compare that with what we have right here. Okay, here we have that exactly, 1 over rad 2 pi, e to the, now the only change here is that this is a s sigma instead of just an s. But notice s was just a real number, s sigma is just a real number. So we're going to take the final answer, and everywhere we see a s, we're going to replace it with a s sigma. Okay, so since the final answer was e to the s squared over 2, here the final answer is e to the s sigma squared over 2. Multiply that by what's on the outside here, and we get e to the mu s, e to the s squared sigma squared all over 2. And that is the MGF of some general normal mu sigma squared random variable distribution. Okay, so that is that's mostly what we're going to say about the normal distribution. In this video, we're going to have a lot more to say about it because the normal distribution and the chi-square distribution have a relationship, and we'll look at it in future videos.